Okay, good morning, everybody. We are very happy to have here Dr. Rohrer, Heinrich Rohrer. He is a friend of us for many years, and practically all of you know him personally, so he doesn't need any introduction. He has done outstanding work in science. He's a very creative man, among many things, and of course, the most important from the recognition point of view is he's the discoverer, together with Binning, of the tunnel microscope, and for that, he got the Nobel Prize. In 1986, I think it's about 5 years after the discovery, we invited him to come here to advise us or to talk with us about NanoGune, mainly with Professor Pitarque, that is the general director of NanoGune, and in addition, for an interview of the Thick Network magazine. From that interview, who was made yesterday, Igor Campillo made the interview to him, and I have selected a few sentences in order to initiate the debate. I want beginning welcoming him as the taxi driver welcomed him. He nearly missed the taxi, of course, because he doesn't know Basque, and he cannot be Niels Borg. Of course, this is transitive in Basque, but he was clever enough to realize that it must be him. Almost missed by an inch. He was saying yesterday that, in his opinion, attitudes of a scientist to do with science: open mind, focus and concentration, and hard work. And an open, unbiased mind usually happens either when you are young, so you, or when you have changed your field, some of you. What he means here is, he explained to me, is that, of course, one has to be an expert to do good science. Being an expert is an asset, but a very real danger, because if you are too much of an expert, be careful, be careful. I will say that in Spanish. En la discusión de ayer me acordé de una cita de Lord Salisbury que dice que hay que tener mucho cuidado con los expertos, porque si uno oye a los teólogos o a los obispos, nada es inocente; si oye a los médicos, nada es saludable; y si oye a los soldados, nada está seguro. This quotation I made in Spanish because I know it by heart in Spanish. So. Then another point who comes is that scientists are conservatives, like experts. And something is new, either because everybody thought it was impossible, uninteresting, insignificant, because he insisted many times, and of course I agree with him and many others, that sometimes a very beautiful thing we think cannot be true. If that is important, somebody else will have already done it, no? Maybe it's his point of view with the tunnel microscope, but you can ask him directly. And scientists are often a conservative lot with many bandwagon jumpers. That's I'm sure this will provoke a discussion maybe with the second part of the audience. The great challenge today in nanoscience, growing a given nanostructure at a given position for a given purpose. I think he was saying yesterday that we can place a probe within pico, with a pico accuracy. That is tremendous, no? Because this is 300 times smaller than the atom or something like that. Nowadays, science and technology are no longer separate entities. The transition is continuous. So there is no science without technology, or no technology without science. It's the techno-science some people talk about now. Nano is different. He always insisted to us, and insists both for institutes and persons, that nano is not only smaller, it has to be different if it's going to bring a qualitative change. It cannot be a continuation of micro, just smaller. It has to be different ways, different horizons. The public should understand that science is not democratic. And science by itself is not connected to values, except, of course, scientific values, but the exploitation of science is. I'm sure with this sentence we can have a half-an-hour discussion as well, but it's up to you. And that's a very, now today everybody is talking about indicators, rankings, numbers. People talk about, I have published in Science, instead of saying what he has done or she has done. So this is a very challenging sentence. The important thing should be standards, not rankings. And better doesn't necessarily mean good. That means that competition is not necessarily good, because by doing competition, according to him, you are better in what is already being made, not in new things. And science is too serious to be a race. And the first question of a scientist will be, what will change if it could be done? Only if we have answered this question, we talk about resources or plans or whatever. So to summarize what he says, yesterday, he said, some scientists are paid for what they are doing, that's wonderful. Others do whatever they are paid for. Okay, so, and now, the floor for you. Professor Rohrer will be discussing with students or answering questions, a kind of informal dialogue. Thank you very much, Heinrich.
Okay, I'm sure actually I don't have to correct you in anywhere, anything you say.
I have good masters.
Okay, so can we discuss about anything? About science. Okay, science we always, I think, consider it, when we talk about science, only the technical aspect. But I think the advancement of science has tremendous other impact, tremendous impacts on society. You see, what do we want to eventually, what are we aiming at in biology or medicine? Okay, so
questions. First one, or comments. I'm sure the students were looking, they were telling me that they are looking forward to who is the first.
I think if one is quite honest, one would like to prolong life as much as one can. Now, that would lead to immortality, more or less. Now, that wouldn't be just a problem for the Catholic Church. It would be a severe problem for humanity, you see. Because nothing would go away, but so eventually nothing could come up anymore, except to kill each other. I mean, that's still, I think with the human beings, that's still a valid option, that you have wars and so on. And you would have wars eventually when nobody dies. Okay, so these are these type of questions which I think you should also from time to time, when you wake up in the night, contemplate. Not think about just your equipment or your equations. Or another one is, yeah.
Okay, we begin.
One question, maybe about your work on the STM.
Yes?
When you were working, preparing, were you thinking about that is something important? Or it is some competition, there was some competition in other groups, or just after, when you performed your work, you realized, or some people realized it is important? Or this question, had some pressure, this competition or
You see, I mean, we of course, we thought it would be very important, otherwise we wouldn't have started. That's already, I think that's, if you don't think something is important, don't even start. And don't think something is important simply because you have started. But you have to start if you can judge or if you think something is important, not the other way around. And I think, okay, in retrospect, you see always many things a little bit, how do you say, in a better light than in reality. But you see, at that time, before, let's say, for a long time, inhomogeneities have been considered not important. That's why, for instance, all the imaging methods were momentum space methods, except maybe the optical microscope at a certain level and the scanning electron microscope in its primitive form. But all the others from X-rays to lead in surface science, everywhere, these were all momentum space methods. And momentum space method only makes a sense when something is homogeneous. Otherwise, it doesn't make sense. It has to be homogeneous over a certain minimal length. That's called the coherence length for doing, let's say, an X-ray image or whatever it is. And so when you see, when you make things smaller and smaller, inhomogeneities will play eventually a very important role. And you see, the effect of the inhomogeneities will go up with 1 over the square root of n. So if you take a piece of semiconductor, you have dopants. Take dopants at the doping level of 10 to the minus 18. That means 10 to the 6 dilution. That means a distance between the dopants of about 100 atoms. That's 10 to the minus 6. Now, if you have a micron cubed, then in a micron cubed you have 3 times 10 to the 3. You have about 10 to the 10 atoms. This is correct. A micron cube is 3,000 atoms, each micron. Huh? That's correct. 3,000 to the 3. That's, I think, 10 to the 10, or not? So you have 10 to the minus 6 times 10 to the 10 dilution. So you still have 10 to the 4 impurities. Now, if you take a micron cube and another micron cube and another micron cube, the fluctuations of the numbers of impurities, that's 1 over the square root of 10,000. That's 100. So, or 100. So the error you can make in number of dopants, that's something 1%. And the dopants have now important aspects for, let's say, conductivity and so on, or maybe also for some other purpose, you see. So the fluctuation of an important property you would like to have might be 1%. Now with a 1% you can live, let's say in electronics, you can live. Now if you go down a factor of 10, then you have only 10 dopants. And the square root of 10 is 3. So you make an error from 100 by 100 by 100 nanometer, in this case, of 30%. And that's for many things no longer tolerable. So that simply shows you that the inhomogeneities have a tremendous impact when you make it smaller. Now, in our case, it was in particular the fluctuation in the conductance through very thin oxide layers. Because our friends, the engineers, they wanted to develop, or they were developing the Josephson junction elements for a new type of computer. And that's tunneling junctions. And so one of the central problem really was the homogeneity of the oxide. You see, in an oxide, the change in conductivity is about a factor, I would say, I think it's about between 10 and 50 per single atomic layer. So if at one place the oxide is just a little bit thinner, that carries most of the current and makes the junction very inhomogeneous. So that was my interest. I mean, that wasn't a specific interest why I got involved with it. I was doing something completely different. I was doing critical phenomena, and I think I was reasonably good there, but that was a very interesting field. It was really a topical field. And it was at the top. I thought it was at the top. So in order to make some reasonable contributions, some further reasonable contributions, I would have had to learn new experimental techniques. Now that was simply a judgment. I didn't think it was worthwhile to learn completely new experimental techniques and build up experiment for a field which I saw at the top, but in principle going down. And so I was looking around, and since I was with IBM, I thought finally I came up with the idea, or the idea came about with the inhomogeneities. And at that time, the components in microelectronics were still relatively large. It was only the tunnel junctions where you used very thin oxide layers and where you used the oxide layers really to produce a current. Not like in many other things, like in the CMOS and all the things where you use the oxide layer as an insulator, you see. So that was for me. And IBM, there was practically nobody in IBM interested in it, on this influence of inhomogeneities on conductivity in general and on oxide layers in particular. I don't know why nobody was interested. So that's always the most interesting thing. If you start with something, nobody else is really interested. But of course, it has to have a future. Otherwise, if never anybody will get interested, then you didn't make the right choice.
A question about that: how do you raise an interest in an enterprise, for instance? When you are working for an enterprise, how do you raise this interest? You said that first people were not interested in this issue, and how?
No. When I presented what I wanted to do, then a few got interested, and they were so much interested. Let's say the management, they were so much interested that I immediately could find a new research staff member, and that was Gert Binnig. But before, nobody was thinking about doing anything along these lines. I think they didn't really think it's not interesting, but they didn't think of doing it. So it wasn't sufficiently interesting.
How do you think do you think it's really important where you are, the environment where you work, to make this decision of focus just in one idea? Because now with this race, trying to get more papers published and trying to get more your work to know, it's not really an easy job to change topic and try something completely new, because you have to have some results in a short time. Because if not, you don't have results, then you don't have time.
That's a problem, but again, you see, maybe you cannot from the beginning do that, but once you have a certain reputation even in the company, if people think that you are reasonably good. And then you also get more time to develop something. You see, then they accept of you that you make something riskier. And I think that's quite general. You see, of course, in IBM you had to be good to get a good salary, because the salary was always connected to the performance. It didn't simply be like in a state institution in a certain level. So now in laboratory, two people who started with the same PhD, same age, in the company, after 15 years, their salary could differ by a factor of 2, just depending on their performance. And so, of course, it's always difficult to measure the performance. But I think, okay, where were we?
Yes, the opportunity to get new things.
Huh? The micro. That's it.
I think you got it.
That's wonderful. I go to something in here. Okay, fine.
One question.
Figaro?
Going on with this idea, how do you see the difference between doing research in a company and doing research in a public institution? Because you are mentioning that there's also a strong competition when you are doing research in a company. And this might be not that good for science, right?
Again, I think you cannot exclude the competition aspect. That simply, when you judge how good something is, if two guys come and ask you, let's say, and you only can give one of them the money, then I think you are forced to think about what he's doing, what he's doing. Now you give the money to one of them. But I think, if you want to call this competition, I don't think that this is really competition. You see, you simply come up what you can do, and then somebody has to judge: is it worthwhile to give money for what you come up? And if both are very good in such a place, then I think it would be the duty of the person who has to decide to find money for both. I think that's another approach. Now you probably also cannot do that everywhere, but nevertheless, I think everybody has to make everybody along the line has to make an effort. That the things which are good can be done, and the things which are less good should not be done. And I think probably if I look at all the research done, I wouldn't say half of it, but a big part of it is not very interesting. And yet you find the money. So the competition is mostly among the lower half and not the upper half, you see.
But what's the difference? I think he's asking the difference between a public institution and a private public institution.
I think
you work all your time in the private, and you were saying that now all these private, like IBM, Bells, have abandoned science, and that is bad for science. But what do these companies bring that public cannot? Is that the question? No?
I think
that's another aspect of the question.
Yeah, I think that these companies, I think they just had depending on their size, some focus on what they were doing, you see, in the company. But the clever ones, and I think IBM was a clever one, they realized that it's important, that it's a matter of spirit in the company, whether you let people perform something completely new. You see, it's for IBM, I would say for IBM it was not a necessity to have, let's say, science in this respect. But the fact that they had science reflected a certain, how to say, attitude towards progress, you see. I think the right attitude. So now the difference, finally, I think the difference is on both have, as I said this morning, research institutions have a few pluses going for them. One is you do not have the boundaries of teaching fields or teaching disciplines. You see, this institution, for instance, does not have to do work in a specific area because it is connected to teaching in this specific area. So you have a lot of freedom. I think that's the beauty of a research institution. And that makes that in a research institution you can much easier approach the so-called interdisciplinarity. You see, because you are not bound to any, you do not always have to go through a concrete wall to go to the next discipline. You can get somebody in here or whatever. That's, I would say that's probably the two biggest pluses of a research institute or a research institution. I mean, there are also a lot of research institutes at universities. But there again, either they are more or less autonomous research institutes at the universities, or they just are part, let's say, a fragmentation of a department. Institute for, I would say, quantum optics, institute for this, and institute for this in the same department. You see, these are more just a fragmentation, a specialization of the department. What is, however, in a place like this here, much tougher in any research institution this way, because the quality of the research is the only justification for your work and for you being paid and for whatever. You never can use teaching as an excuse. And research is changing. Teaching is not changing that much. And that's why I think I never have seen a university disappear. But it's I have seen many research institutions disappear. And so, okay. Yeah.
So I would like to ask for a little advice for us young researchers. What do you find about the specialization? So we have to decide in some years to choose for a postdoc and so what would you advise us to a specialization?
Okay, I would say the first thing is do what you think is worthwhile doing. And if you are judged to be a reasonable scientist, then a reasonable professor or a reasonable director, that's now meant as an example. will let you do it. I think that's the more. If you ask always other people, somebody said once, for every creative guy, there are at least 10 creative killers, creativity killers. And that's the way it. So do what you think is worthwhile doing. But for this, you have to make an effort of finding something which is worthwhile doing. And not simply wait till somebody tells you what he thinks is worthwhile doing, you see. Concentrate on that. Another aspect, when you are just at this year, we had many PhD students and postdocs at the IBM laboratory, especially, let's say, in the last 20 years when I was there. And the PhD students, they came from the Institute of Technology in Zurich, the ETH, or from the University of Basel, sometimes even from German University or somewhere else. And I think most of them have made quite a good scientific career. But I would say the best ones now, the best professors, I think are those who changed their interest, or let's say, when becoming a postdoc. They went to a place and did not simply rebuild the apparatus they used in the other place for their PhD work and continue this field. They did something new. Of course, they were not, maybe at the beginning, a little bit at the disadvantage because they had to do new things. And that's also what we did in IBM, the new research staff members. I think especially in physics, we did not select because we wanted to be some experts in a certain field, they should continue. We simply tried to find the guy who is most versatile in interviews, you see, and let it then up to him what he would like to do. Of course, we could not provide any type of infrastructure, you see, whatever was possible. That was certain boundaries. So in our place it was solid state physics. If somebody wanted to play around with liquids, he also could, you see. But I think he could not really make a life with X-ray scattering in the institute. Then he would have to find some accelerator or some machine. If this was the case, if he had good ideas, I think once we took one of them, and he spent most of his time at the synchrotron, you see, and that's possible. So that's also already by the choice of young or of new research staff members and also of postdocs that the first who counts is their ability, and only second their speciality. Of course, the ability has to have some connection, as I said, with certain fields. And, but somebody who is really, as a scientist, stable, I think he can enter nearly everything and be accepted scientist within 2-3 years.
I mean, in this world, it's really important to have a reputation. And do you think it's more difficult to have a good reputation if you change topic often, or if you always keep in the same topic and you're an expert and you're the best one in that topic? Maybe it's easier to have a good reputation. At least the people in this topic knows you.
Yeah,
then you have more easier.
Yeah, you probably, I mean, there is not, I don't say changing topics makes a great guy of you. And not changing anything makes a bad guy of you. But I think if you have the guts, the courage to change, and you have the courage, if you think you are good enough, you can do it. You see, you will succeed. Then I would advise you to make changes from time to time. I made with IBM 3 major changes. And in each field, I finally moved up to somebody in this field. And then the third field was then the STM, or this area. And there, in each field, when I started, I was absolutely a nobody. That's when you go to conferences, you are a nobody. But if you have something reasonable to say, you are already a somebody next time. And you are a somebody maybe the time afterwards. So changing a field, I think, is very helpful. and makes you young or keeps you young. But you have to have the courage to do it.
What do you think is one of the more interesting hot topics in science? Is one of the more interesting hot topics in science today in research?
You see, in principle, I should have a hearing aid. But I usually forget it. That's why I talk a little bit louder. If you think the publishing or not?
No, what do you think is one of the more interesting hot topics in today's science?
That's a hard one.
I think that's what you should decide. You should decide for you.
Yeah, but I asked for your opinion.
She wants to know your opinion. She has her opinion.
Now you have an opinion.
Yeah.
What opinion?
No, I have not yet. But
I
I
am
want to know.
That depends in which area. Now, since I have nothing to do with elementary particle physics and so on, I cannot really judge. But I think their hot topic probably is to find the Higgs particle. Then there are probably, if you look at astronomy or astrophysics, they have probably also 2, 3 hot topics. I don't know. And then if you look at us poor guys, I think everything which has to do with the small scale, with the nanoscale, could develop really into a hot topic. And biology, I think, is already as hot topic, is, I wouldn't say on the way down, but no longer really on the way up. What still might be on the way up, or probably is, that's brain science. Not from the point of view of the, how do you say, physiological action, but from the point of view of how do you say, creativity and so on. I think that's, if I would have to choose now, just a new field, I probably would choose brain science. And not the biological approach of brain science, but a little bit a different one.
But that's what Josephson was doing.
Huh?
Another Nobel Prize was doing that, right?
Yeah.
Josephson.
Okay, Aris.
Okay, I still feel curious about how science is made in big companies such as IBM and how the scientific freedom. So at some point did you have to keep in mind any kind of profit of your ideas so that the company would get a profit, or you could have a very good idea but with no profit and you could go ahead in that idea?
Okay, again, IBM at that time, they simply said it has, for the people in physics, for instance, in our lab or in the big laboratories, it has to be very good science or vital to IBM. So you could choose. If it was both, it was even better. But you never had to make, let's say, do something which was, let's say, unambiguously connected to a product. That might have changed a little bit, but or maybe a little bit more. But you still have room for thinking about something without thinking of a specific product. Now, if you look at nano, I think most of nano is in one way or in another connected to some process or to something which might prove useful. You don't know what, but it might. It probably will. if it's so as soon as you, okay, let's put it this way. The last couple of years I was with IBM, we thought of the millipede. And the millipede, we called it a storage device. And the slogan was, a petabit in your pocket. The millipede is the following. I mean, you know, an ordinary disk turns round and you have a reading head. A millipede, you have an array of these cantilevers. Maybe we thought of 1 million. I think now in a prototype they made now 10,000. So you have 10,000 of these cantilevers, 100 by 100. And each one, you have more or less the same medium. That's a polymer. And each one makes small holes into the polymer. And so, if you have this 100 of 100, what you do is just moving the whole storage medium by one cantilever, and you scan it this way, you see. So that's a different approach than the normal storage. The access times are much smaller because you only have to shift much. The reading speeds, even if, you see, the reading speeds are of each cantilever is not very fast. Let's say what they can do is maybe 100 kilobits per second. That's of course nothing compared to a magnetic disk. But each cantilever can do that. And so when you do the multiplexing of the cantilever, that this works, this works, this works, this works, you see. And you take a multiplex cycle of 1 second for 1 million cantilever, each working at 100 kilobits per second. You have a reading or a writing speed of 100 gigabits per second. And that's way beyond any other thing can do. Now, and it can be made very small. So we sold this to IBM from this point of view. And of course, they liked it. And so they are working now 10 years on it, and maybe it really is a new product, maybe not. Because it's a completely different concept and architecture than conventional storage. That's, you have to do, okay. Now, I think the real significance of the millipede is not just being a very, very fast and dense storage device. You could now imagine that here you have the polymer level, here you have the cantilever level, and then you have a next level. That's where the level where you can connect the input and output of cantilevers, where you can do some type of rudimentary processing. Can be rudimentary, can be less rudimentary. So this would mean you would then have a computer architecture where storage and processing, it would be some type of storage processor hybrid. And where do you have storage processor hybrids? That's the brain. The brain is a storage processor hybrid, you see. Brain is not just a storage device, and it's not just it's a hybrid. The brain is on the bit level, a hybrid on the bit level. The millipede is a storage processor hybrid on the megabit level. But, okay, nevertheless, I think even on the megabit level, this might give you different opportunities for doing something. And so that was my interest in the whole. Okay, we couldn't sell this to the company because they They would be too stupid to understand it. You see that, but that simply shows you I think that's one of the how do you say, characteristics of good science. That when you do something, that you can go a step further than your original aim. You can do afterwards. It fans out into many different possibilities. I think that's one of the how would I say, the very good approach to science and technology.
So when you mention this thing of the science, I can see, maybe I can see here, this sentence, I will read it to you. Oh, dear. That is, with my ability here, okay. I can take, okay, no. Okay.
Open mind.
No. I wanted to ask you about this comment you made about the values. We have here some people saying that, of course, science influences the values of society, not only because of the scientific values, because it creates a different perspective, a different horizon, as you said, and therefore the values of today, in part due to science, are different from the values of yesterday. But you seem to think that there is a separation between science and values, no?
Okay. I think that's correct. No, it's, you see, science has its scientific values, but it does not have a priori society values or ethic aspects. I think I better would talk about aspects but than values, you see. I think it's not reasonable to say science is not ethical, you see. But I think it's not just according to some ethics. Because there are two distinct steps. One is the scientific achievement per se, the scientific, disconnected from anything else you can do with it. And the second one is the exploitation of science. And there is nothing on the world which you cannot use in this respect or in this respect, you see. You can use this in many ways. You can read a devastating letter with this one. But you can use it for a reasonable communication, you see. The thing selber is innocent. It's how you use things. So we have to see that science keeps its innocence. And there we have to make an effort that we do not start cheating in science, for instance. I think that's one of the dangers for it. But otherwise, you see, that's something against the scientific value if you cheat in science. That's not. So from this point of view, that's one thing, and on the other hand is the exploitation. Now the question comes always up, a question comes up, it's not just the questions. People start to interfere with science. Politicians, organizations and so on, they want to interfere with science, you see. And I think that's nonsense. Because they only have to see one aspect and they you can easily kill off. A question comes up, it's not just the questions. People start to interfere with science. Politicians, organizations and so on, they want to interfere with science, you see. And I think that's nonsense. Because they only see one aspect, and you can easily kill off a tremendous importance of a new scientific development just because you think one implementation of it could be very harmful. That's one thing. Then I think neither politics nor society, and not even science, know what we need in 20 years. And that's the way it always developed. We cannot say what we need in 20 years. Maybe we have to do certain things in 20 years, which we think nowadays are a little bit critical, if we use it nowadays for a certain purpose. But maybe we have to take biology, you see. We wouldn't be anywhere if people wouldn't have worked in biology 50 years ago, without knowing whatsoever that there will be once AIDS, that there will be the Parkinson disease, or okay, that probably, but the AIDS I think was not known. The bird flu was also not known, and all these kinds of things. So there are a lot of things which are simply not known. And science may, or let's say we had all the progress because science was always quite far ahead. When Ampere and Ørsted and so on, these guys made their experiments. They didn't think and didn't know that maybe 200 years the world really depends on electricity. We simply didn't know. When the guys found the optical microscope, nobody thought, or these guys did not think of the complete change and opening of biology through the optical microscope. Biology came about because of the optical microscope. We simply have to recognize that. Today's lithographic techniques are just, the reverse of an optical microscope still. Nobody ever thought of, 40 years ago, or when was it? The first 85, 80, 60, 48, 58, 68. The transistor came from 48. And in 68, 70, the first integrated circuits in this sense came up, you see. So all the people who studied semiconductors during nearly 100 years. And the major interest was simply the scientific, that semiconductors behaved very much different from normal conductors. It had another temperature dependent, in many ways different. Then they had to learn that in order to get better conductivity, you have to dope it. Whereas in a normal conductor, it's just the other way around. So these were very interesting property. And so they learned, because they learned how they develop processes. One is the zone melting, you see. The zone melting was invented long before the transistor came up. But all this progress in science, not for the sake of transistor, were extremely important to develop electronics on the basis of transistor. Okay, yeah.
Danny.
I have a question. Actually, all what you said, you just said it's a praise for freedom in science, and I fully agree with that. But I'm curious to hear your opinions about the popularization of science, and particularly the interaction between technology and science, because there is a clear way in which society, besides the technical, the ethical aspects, there is a clear way where society influence, which is funding. I mean, you need funding to do science, and for example, now society is asking for applications all the time. I mean, we have to claim that everything that we do will give some application immediately. So, I mean, how you see this connection? How science should be funded, should be organized, and how it should be related to this prospect for applications?
I hope in this institute you do not have to explain what gadget you want to make out of what you are doing.
You don't have to. Well, Danny.
Okay.
Well, what do you mean by well?
I have heard it.
Not to Pedro, but to the funding agencies, of course, we have to say that things that we do are useful, but in a very clear way, very applied way.
But you see, every science has to be useful. If it's never used, then it's not worth doing it. Yeah. Just like every experiment, if you not really know what you did, it's also useless. If you cannot explain results, you see, then it's useless.
That's quite strong. That's quite a strong statement, isn't it?
That's correct. Okay. Oh, think about it.
Yes, sometimes it takes years to understand and explain an experiment or things that people did in the past, and at this past time they thought that they were useless. It took us like 40 or 50 years to fully realize what happens with these things.
That's why I said ever. I didn't give a time scale. I just said if it's never used, then I think it was useless. Now the time scale, that can be really different. And it's difficult to justify, not just against the public, but even against the scientific community. If nowadays, if you don't see anything, if in 20 years or in 30 years. Now, of course, it depends what the objective was, you see. If the objective was just to find the Higgs particle, then I think it shouldn't take more than 20 years, maybe it takes longer. But that doesn't mean yet that the Higgs particle by itself might be very useful. Now, if we always say, more or less you can believe into the fact that if something is new, it sooner or later will become useful. Sooner or later.
Do you think that there is still space in physics, at least in theoretical level, to have some great advances? I mean, in the beginning of the century, for the 2-3 decades, there were great advances in theoretical physics, which we just see the consequences and the applications. Do you think that there is still space in theoretical physics for great advances?
Sure, otherwise you wouldn't have to do it. And you see, at any moment, people can say, okay, that's the end of it, and that's what very often happens. Now, if you just ask me, if somebody would have asked this after Einstein in the 20s, probably nobody would have thought of coming up with quantum mechanics. You see, quantum mechanics was something completely different. In the theory, people did not anticipate anything like that. Now, since we have quantum mechanics, what could be something new? I always favor quantum mechanics is fantastic, but it's always a one particle affair with interactions. It's not, except maybe in the superconducting state, but otherwise. So maybe we find once a way to solve a 10-body equation as a 10-body equation, and not with 10 single-body equations and 1, 2, 3, what is it, 10, not 10 factorial, but nearly interactions, you see. I think also for theory, the sky is the limit.
Well, actually, I won't insist on this specific question. What I mean is the following. We have compartmentalized physics. We have fragmented. I mean, we can be physicists on the same room, and you go to a seminar and you attend the physics which is on a different part of physics, and it's like you speak a foreign language. So in the beginning of the century, all these physicists looked like they made advances that they affected globally physics. Is there space for such advances in nowadays?
I don't see any problem. You see,
the fragmentation, this is what I mean, of the specialization in very narrow areas, doesn't it impose restrictions in fighting things that affect physics globally?
It does, but that's also the problem with experimental physics, you see. I think you just have a pencil with an experiment, you have to design an experiment and whatever it is. And you can use your brain. So from this point of view, you see, I think also experimental physics aims at explaining phenomena. On the basis of the fundamental laws of physics. And see what you can do out of the equations with the fundamental laws of physics. So the fundamental laws are, of course, that's not what we have, the thousands of equations we have in the textbooks, which are usually just for some specific case. So from this point of view, whether the experiment is now the verification of a theory, or whether a theory explains an experiment, and maybe by explaining it in certain terms, it has to introduce something new. And then the theory might then open again a new aspect for which you have to make experiments again, or a new aspect on which you can play around with theory.
Okay, 1 or 2 more questions because we are already past the hour. Last question.
Talking about relations between society, technology, and science, and well, I think that the role of society, and Danny said something about it, it's important in science. They are influencing somehow. So, but I see that there is still a huge gap between society and science. What kind of science to bring the science to the street, to make public to understand it somehow?
You see, the gap is about, there are two, the gaps are made by two aspects. One is about 10 to 15 years of studying. That's simply a gap. If it's not a gap, then I think it would be a pity. And the second is the brains who can study Compared to the brains, you cannot. That simply widens the gap. So there is a gap. We cannot do anything about that. Now it's very difficult to make society understand what we sometimes don't understand either. Sure, you can try now to make them understand a few things. You have to be very careful that you do not overdo it. You can simplify things a little bit, but if you overly simplify it, then you have to, let's say, you have to draw the attention to the fact that this is now just applicable to this case. I think these are the things you can do, and we certainly can make an effort. But I think the major effort also we also have to make is to make society understand that it's the decision what you do with science which is the important aspect of society and which is the responsibility of society, not of the scientist. You see, the scientist, once you have said something, that's open. That's public property, or how do you say? That's if you have said something. Probably already if you simply have thought something, because usually your thoughts will come out in one way or in another. Because you never can take a thought back. But what you make out of it, that's really an open field. And I think the public has to, then the public can blame industry. But their industry has, maybe they have a certain also responsibility. But you see, the industry only makes these products which they can sell. If the public doesn't buy, the industry doesn't make it. Now it's not just the public. If a government doesn't want to have atomic weapons, nobody in the country makes an effort to produce atomic weapons. I mean, let's say, as in Spain, for instance. So it's always the exploitation of science which is the responsibility. Now the scientist, maybe he has a certain experience about something, he sees what the exploitations can be. And he can say, listen, you can do it this way or this way. But then the scientist has to, I think the scientist always has also the freedom to do what he wants to do. That also means to work where he wants to work. So I know a theoretical physics. He came from Sandia. That's one of the big weapon national laboratories in the United States. So he was a very good theoretician. So he simply said, I have enough. I don't want to do it. And went to Seattle. Sandia is in Albuquerque. He went to Seattle, then got a minor position in the faculty for dentists. And so he did a few things, and then he developed a few very fantastic things, not about the dentists, but about theory about, let's say, the possibility of using the the magnetoelectric coupling. The magnetomechanical coupling of a cantilever with a magnetic tip to a nuclear moment, which is, he developed a theory, and I think he could show that eventually we could get to this precision, and if we can, it would be fantastic. So you see, this guy simply made the decision where he wanted to work. And I think that's still open for the scientist, where he wants to work.
Okay, last question.
It's a short question, like philosophical questions. After science, after prize, after the many honors, after the normal life of a scientist, which things are so important for the man Heinrich Rohrer? I think is the question. Which things, which values, which aspects it's so important for you?
Besides science.
In science.
As a scientist.
After science.
After science.
As a man. As a person. No?
Oh,
Yes,
I would say A is die in peace.
Die in peace. Very good.
That's one thing. I think now, sure, now I have become more of an egoist. So I think my health is probably the most important. But then I suffer when I also see other people suffering. I would say of the most important questions, for me, I think is or finding a solution to the widening gap of society. You see, we talk about North and South, or we talk about rich and poor. But now even more, we talk about dumb and clever. That's something which is really threatening, because technologies and everything gets more demanding on the brains than ever. And so many brains can no longer cope. So what do we do with all the people? We can use a few of them to dig holes, but not all of them. We also replace digging holes by machines. So you have to be able to operate the machine. Now, do we make enough efforts to make technology, modern technology also how do you say, open to those people, you see? And I think we don't. That's very clear. I think if you just look at programming a computer, I see what difficulty I have with a computer, you see, because I didn't grow up with a computer. So my generation, I think, now I'm even a scientist, and so I maybe have a little bit a better flair of doing these things. But so many people couldn't do it, you see, and that was a problem. And the problems will, I think, always these developments go exponential. There is no way around that. And so I think that's probably one of the most serious problems. That's the knowledge and know-how gap, which will hit not just North and South. It will enhance the gap between North and South, for instance. But I think it starts to open a lot of gaps in your own environment. And that's where we have to think a little bit about it. So far, neither industry nor anybody thinks about it. People happily buy radios and telephones and so on, but somehow they do not go beyond and see, okay, it seems now everybody can use a handy. But that's a simple. So can we make many other things that simple?
Thank you very much.
Okay, so thank you very much for your time and excellent conversation.
Thank you.